call it T. Okay. Now, little a, let that be the input symbol you read in the first move. So your string X goes in, the first symbol you read is a little a. Right? That's what you're saying here. And the last symbol that you read, that's a little b. That's in the substring X. The last one you read is a little b. Okay? That's what you're saying here. Now, let little r be the state of the machine, the PDA, after you read the little a. In other words, after your first step. Okay? So this is like the next state after your p, little p. You start in state little p. Okay? So R is the next one. Okay? So that's the state after the first move, the first step. Right? And let little s be the state just before the last move. So you read your little b, that's the last symbol that you read in your X, substring X, okay? And then you'll switch to state Q, right? So S is the state just before you switch to Q, right? It's the state just prior to state little q. Alright, now it's a PDA doing that. Right? So you must have transition rules, because PDA, right, of the following form. Now, so you're in state P, you read A, that's your first symbol, okay? You don't do anything with the stack, epsilon, and then the next state is little r by definition, right? So it goes to state R, and you push T on the stack. Remember, this stack does not empty between P and Q. It only empties when it goes to Q. For the first time, it empties, right? So that means the symbol that you push at the first, when you read the first symbol, is equal to the symbol that you pop at the end. And we said that was T. Okay. So you're pushing T here, right? And you must have another transition rule that will take you from state S to Q. Okay? So this ordered pair must be a member of this transition rule. Okay? Remember, transition rules in PDAs, non-deterministic PDAs, are sets of ordered pairs. So you're going from state S to Q. So this will be Q. Let's see, and you're reading a B, that's the last symbol in your substring X, yeah, that makes sense. And what's on top of the stack? Well, T, so all that fits, and therefore this will give you that as the output to the transition rule. And so you just change state to Q and do nothing with the stack, because here you've popped it. And you've popped it. Once you've popped it, you can't. It's a machine that can only pop or push. Can't do both at the same time, and it can't do nothing. Right? Like there are four possibilities. Right? It doesn't push or pop. It pushes, it pops, or it pushes and pops. Well, the first and fourth can't do this machine. It can only push or pop. Right? So here it pops and then does nothing. Yeah, that's what epsilon means. You ignore, do nothing, ignore it. All right. Okay, so here's your string X. The first member of X was A, and the last was B, and let Y be what's in between, whatever. Okay. So X is A, Y, B. Now, so this Y, what's it doing? Well, it must take your machine, your PDA, from state R to state S, right? Because your B, now why is that? Because of here, because of that. Right, so now so this Y here doesn't change the the stack, right? So your T is left there. It was pushed when the machine read A, and it's still there and gets popped when the machine reads B. So the processing of the machine as it reads Y leaves the T on the stack from here and pops it here. Okay, so the stack is now empty. Okay, so that means that the machine P, it can go from state R, right, to with an empty stack, to state S with an empty stack on reading this Y. Okay. Now, so what's happened? So we read in K plus. No, we took K plus 1 steps to read in this. Okay. Now these correspond to 2 steps. The reading of those two. So the reading of Y will take K minus 1. You subtracted 2 from K plus 1. Remember your processing this, we assumed at the beginning, takes K plus 1 steps. So processing this one, the Y, will take K minus 1 steps. That's 2 less. Okay? Alright. Now, the induction hypothesis says that you can derive from state R to S in less than K steps. Well, in fact, we've got K minus 1. So we can do that by the induction hypothesis, right? Well, we know how we can do that in 1 step. We can do that in 1 step, and we can derive. We can generate this with our grammar, right? Because we know we can do this. That's in our rule set, and we assumed it's true by the induction hypothesis. All right. Well, so if we can generate the string Y from this, going from state R to S, that from that variable from this variable we can derive Y. Well, since X is A, Y, B. So the grammar APQ. Now remember, APQ is A, big A, RS, little b. So we can from this derive X, because X is A, Y, B. Okay, so that's that done. Alright, now in the second case, that's when the stack empties more than one time between states P and Q, right? Let's see. So when the state does empty for the first time, let's say the state is in state little r, okay? So you go from state P to little r, and then in the second part, if you like, it'll go from state R to Q. Let's say it just empties twice. If it's more than that, well, you can generalize the argument. But let's say it just empties twice. So first time the machine will go from state little p to R, and the second time will go from little r to Q. Okay, and each of these processing times will be less than k plus 1. Okay, so since this kind of argument, that can be done. That's part of the induction hypothesis, because going from P to R at most k steps, and going from R to Q at most k steps, and so it can be done. You can derive the string from the grammar in less than k plus 1 steps, and since APQ there's a rule in the rule set. Well, look, I'm going to the next section, so I'll stop here and just continue on.